Okay, we've now reached the most important theorem of this chapter, and that's called the Martingale convergence theorem. What this theorem tells us is that if I have a martingale, it really wants to converge a martingale in L2. As soon as it is in L2 in a uniform way, so the supremum of the L2 norm is finite, so as soon as I have this form of boundedness, then I actually have convergence. There exists a limit in L2, and the convergence to that limit of Mn occurs both in L2 norm and also almost surely. So that really tells us that all sorts of approximations will be converging as long as they remain martingales. And that's going to be very helpful in applications, in particular in the development of an integration theory. Now let's have a look at the proof. So I want to prove that my martingale, that is uniformly in L2, has an almost sure limit. So really what I'm trying to show first in this proof is that the set of all omegas such that the lim inf of the Mn, which exists because it's a lim inf, has to be not equal to the lim sup of the Mn of omega as n goes to infinity. So I need to show that this set has probability 0. Okay, but if the lim inf is not equal to the lim sup, then there has to be a gap between them. So this set, the set where lim inf of Mn is not equal to lim sup of Mn, that set is included in the union over all rational ABs, let's say, such that the lim inf of Mn of omega, okay, is smaller or equal to A, which is strictly smaller than B, which is smaller or equal to lim sup of the Mn. Right, if there is a gap, then I can fit a interval in that gap, and that interval I can fit a possibly smaller interval with rational endpoint by the density of the rational. So I'm going to call this set, let's say AAB. And because I'm taking a countable union of such set, it is sufficient to show that every one of them has probability 0. Right. Yeah, A was less or equal to B in the definition of that set. Right, so let's try to show that such a set has probability 0. So I'm going to define delta to be the size, actually half of the size of the gap between these two things. And okay, so what does that mean? That the lim inf is smaller than A, that's strictly smaller than B, that's smaller or equal than a lim sup. Right, well, that is really going to happen if when I can find some k in the natural numbers and I can find some m in the natural numbers, and let's say I'm going to take k greater than m such that the gap between these two is at least delta. Right. If the lim inf is going to be smaller than the lim sup with a gap that is b minus a, then for large enough values of k and m, I need to have a gap that is at least b minus a divided by 2. Okay, now what is that? Well, I mean, it's the integral of the indicator function of that set. So this is certainly smaller than, that's sometimes called Markov inequality, and I'll let you check that if it doesn't seem obvious to you. This is certainly smaller than this quantity, 1 upon delta squared times the expectation of the variable that's large squared. Okay, that's fine. Now this starts looking like something to which Dub's L2 inequality could be applied. All I need is really to have a martingale in here. So I'm going to rewrite that as 1 upon delta squared times an expectation of supremum, let's say for j in n of mj plus m minus mm. Right, and I could fix my m to start with, actually, because it's the lim inf being smaller or equal than the lim sup, so the lim sup is going to be greater than any value of mm. So I'm fixing an m, and I'm taking this sup. Now, I'm claiming, which is easy to say, that if I define m, I should not use a star, m tilde j to be mj plus m minus mm, then m tilde j is going to be a martingale. Right, because mk is a martingale, and that's a martingale that will just start at 0. Okay, so I can apply Dub's inequality, Dub's L2 inequality, and control the expectation of this maximal function by the supremum of the expectations. So control that by the sup over j of the expectation of my m tilde j squared, which is really mj plus m minus mm squared. Right, so this is the probability that I have here, and what can I say about it a bit further? I can rewrite that as the expectation of a sum from k running between m and m plus j minus 1 of the martingale difference, mk plus 1 minus mk squared, right? Because this series is telescopic. Now, that's where we're going to use a very important geometric properties of martingale that we haven't quite discussed at this stage. And this probably is the fact that the increments of a martingale are orthogonal in an L2 sense. So let's see that. And that's going to allow us to massively simplify this expression here, right? Because this expression here, if I were to expand this sum squared, I will get all sorts of cross terms. But actually, I won't get any cross terms because of the orthogonality of the increments. So let's have a little digression here and show this fact. So let's introduce some notation. Let dk denote this increment, or this difference, this martingale difference of the mk for all k in n. And my claim is that these differences are orthogonal in the sense that the expectation of dk is 0 for all j not equal to k. Now, to prove that, let's say that j is greater than k. Obviously, the case k greater than j is treated exactly the same way because j and k play a symmetric role here. And so what have we got? Well, one trick we use very often when dealing with martingale is conditioning over a well-chosen sub-sigma algebra. When I'm computing an expectation of random variables are the same as the expectation of their conditional expectation over whatever it is I want to condition upon. And that's a consequence of the fact that omega is in every sigma algebra, so sub-sigma algebra. So what I want to condition upon here is fk plus 1. Now, why do I make this choice? Because fk plus 1 is going to see, well, dk and dj very differently. dk is going to be fk plus 1 measurable because it's mk plus 1 minus mk. But dj is not going to be, because dj contains mj plus 1. J plus 1 is at least k plus 2. So dj is not, in general, fk plus 1 measurable, whereas dk is fk plus 1 measurable. So if it is fk plus 1 measurable, I can use the take out what is known property and get that this expectation of the product is really dk times the conditional expectation of dj given fk plus 1. But I know exactly what the expectation of dj given fk plus 1 is, because mj is a martingale. So when I condition mj on fk plus 1, well, when I condition mj plus 1 on fk plus 1, I get mk plus 1. And when I condition mj, which is at least k plus 1 on mk plus 1, I get mk plus 1. And that's it. That's why the expectation of dj times dk has to be 0. So I have orthogonality of the Martingale differences. And that's a very helpful result, because going back to what I was trying to compute here, eventually, I'm looking at increments of the Martingale, possibly larger ones, because I'm talking about the limit. So I'm looking at any size increment, like, reasoning about something being a Cauchy sequence. The way I can see a large increment of size, size j here, is as a telescoping sum of increments of side 1. And now this orthogonality property of the differences is going to allow us to very nicely simplify the expression for the large increment as a telescoping sum of increments of size 1. All right, so at the end of this digression, what have we got? Let's remember this formula. So we have that the probability of AB, and remember I'm trying to show that this is 0, is smaller than 1 upon delta square supremum over j in n of the expectation of, well, it should really be a double sum, k equal m to m plus j minus 1, and a sum L equal m to m plus j minus 1 of the expectation of dk dl, but then this is going to be 0 unless k is equal to L. So what I'm getting really is 1 upon delta square supremum over j sum over k from m to m plus j minus 1 of the expectation of m, what is it? mk plus 1 minus mk squared. Okay, now what can I say about that? Well, it certainly is smaller than 1 upon delta squared times the sum from k equal m to plus infinity of the expectation of dk squared. Now, this may or may not be finite, but we're going to show that it's finite, and in fact it is the tail of a convergent series. So if I send little m to infinity, then I'm going to get 0. Now, how do I see that this sequence is converging? So let me write that up. First of all, we have that if this series happens to converge, then the probability of AB will be 0, just sending little m to infinity in the expression we've got here. Now, I want to show that the series of number is convergent. And how do I do that? Well, I give myself, well, it's a series of non-negative numbers, so I just need to show that the sum from k equals 0 to some n remains bounded. And why is that? Let's give ourselves an n. Let's compute the sum from k equals 0 to n of the expectation of dk squared. I can rewrite that as a double sum k equals 0 to n, L equals 0 to n of the expectation of dk dl. That's because of this orthogonality property that we have seen earlier. And now I can get the double sum inside the expectation, and I will get that this sum of the expectation square is really the expectation of the sum of the dk, k equal 0 to n squared. Right, but now this is still a scoping, right? Because dk is mk plus 1 minus mk, so this is nothing but the expectation of mn plus 1 minus m0 squared. And whatever that thing was, this is the L2 norm of mn plus 1 minus m naught. I haven't told you if m naught was 0 or not. Usually we initialize things at 0, but we haven't done that here. This would be squared. I'd rather not square it, so let's raise everything to the 1/2. And now from triangle inequality, in L2 I get 2 times the supremum of the mn in L2, and we know that's finite. I should not use n L, because n is some fixed number that we've got here. So we know it's finite because that's exactly our assumption. That's where our assumption kicks in. Our assumption guarantees that this sum of the expectation of dk squared, so a sum of the variances of the dk, we have mean 0, has to form a convergence series. And because it has to form a convergence series, that makes these quantities go to 0 as m goes to infinity. M was arbitrary, and that gives us that the probability of this set is 0. So we have proven the existence of a limit, right? We've proven that the set of omegas for which the lim of mn is not the lim sup of mn has probability 0. That is to say that with probability 1, the lim fits the lim sup. So with probability 1, the limit exists. So we have proven that there exists a limit, and let's call it m infinity. Exists m infinity. I don't know yet whether or not that limit is in L2, but this is certainly measurable as a almost sure limit of the mn, such that mn tends to m infinity almost surely. Now we have to say that this limit is actually in L2, and we have to see that the convergence happen in L2. Now, why is that? Well, I'm going to take a little m in n, and I'm going to consider the expectation of m infinity minus mm squared. Now I'm going to show that this goes to 0 as little m goes to infinity. Now, this may be infinite, but of course, if I show that this is less or equal than something finite, then it will have to be finite. In particular, my m infinity would have to be in L2. Now, what is this object? Well, almost surely it is the limit as n goes to infinity of mn minus mm. And this can be rewritten as the limit of a telescoping sum, which is the sum j running between m and n minus 1 of the dj squared. Right, now, okay, so it's the limit of such an object. The sum of the dj squared, that's a non-negative variable, so I can exchange the limit. Worst case scenario, I'm controlling by plus infinity and I get no information, but we'll see that. So we're not controlling by plus infinity, we're very much controlling by something finite, in fact by something that goes to 0 as m goes to infinity. So this is controlled by the expectation of the sum of the dj squared, j equal m to n minus 1. And now I'm using the orthogonality again. The expectation of the sum squared is really the expectation of the sum of the squared, because all of the cross term are 0. So this is the limit as n goes to infinity of the expectation of the sum j equal m to n minus 1 of dj squared, and that is certainly smaller than the sum j equal m to infinity of the expectation of the dj squared. And we have seen that this series of numbers converges. So not only is this finite, this also goes to 0 as m goes to infinity. And that tells us that m infinity is actually an L2 of omega sigma p, and the convergence of mn to m infinity is not just a normal short convergence, but it is also a convergence in L2. And that concludes the proof of the Martingale convergence theorem.